Okay, so once again, good afternoon. So for today, we're going to discuss about the introduction to asymptotic analysis. So algorithm complexity is a very important topic in computer science and IT. So knowing the complexity of algorithms, allowing you to answer questions such as how long will a program run or an input, how much space will it take, is the problem solvable? No, these are important basis of comparison between different algorithms. So an understanding of algorithmic complexity provides programmers with an insight into the efficiency of their code. So complexity is also important to several theoretical areas in IT and CS, including algorithms, data structures, and complexity theory. So asymptotic analysis, now when analyzing the running time or space usage of programs, we usually try to estimate the time or space as functions to the input size. Let's say, for example, when analyzing the worst case running time of a function that sorts a list of number, we will be concerned with how long it takes as a function of the length of the input list. Now, let's say, for example, we say the standard insertion sort takes time, not capital T opening close parenthesis n, where capital T opening close parenthesis n is equal to C as multiplied by n squared plus k for some constant, no, say and k. So in constant merge sort takes that capital letter T opening close parenthesis n is equal to C, no, multiplied by n multiplied by log 2, no, multiplied by n plus k, as what we already use in our
mura na yun, 1.9. Mura na yun. Eh ba nga, 2.5 yun eh.
nagbibenta.
Sama na doon, smoke.
Pamute po.
Okay, so again, as I mentioned earlier, no, the asymptotic behavior, no, of a function or f multiplied by n, such as f multiplied by n is equal to C multiplied by n, or f multiplied by n is equal to C multiplied by n squared, and others. Or it refers to the growth of f sub n or functions as an n gets large. So we typically ignore small values of n since we are usually interested in estimating how slow the program will be on large inputs. So a good rule of thumb is that the slower the asymptotic growth rate, the better the algorithm. So although this is often not the whole story. So by this measure, a linear algorithm, no, is always asymptotically better than a quadratic one. That is because for any given positive C, K, D, and Q, there is always some n in which the magnitude of C multiplied by n squared plus Q overtakes D multiplied by n plus K. So for moderate values of n, the quadratic algorithm could very well take less time than the linear one. Let's say, for example, if C is significantly smaller than D, and or K is significantly smaller than Q. However, the linear algorithm will always be better for sufficiently large inputs. Remember to think big, no, when working with asymptotic rates of growth. So, worst case and average case analysis. When we say that an algorithm runs in time, no, multiplied by n, we mean that T multiplied by n is an upper bound on the running time that holds for all inputs of size n. And this is the called worst case analysis. The algorithm may very well take less time on some inputs of size n, but it doesn't matter. No, if an algorithm takes capital T multiplied by n is equal to C multiplied by n squared plus k steps on only a single input of each size n and only n steps on the rest, we will say we still say that it is a quadratic algorithm. So based on your college algebra, no? So a popular alternative to worst case analysis is an average case analysis. And here we do not bound the worst case running time, but try to calculate the expected time spent on a randomly chosen input. And this kind of analysis is generally harder since it involves probabilistic arguments and often required assumptions about the distribution of inputs that may be difficult to justify. On the other hand, it can be more useful because sometimes the worst case behavior of an algorithm is misleadingly bad. A good example of this is the popular quicksort algorithm, whose worst case running time on an input sequence of length n is proportional to n squared, but whose expected running time is proportional to n log n. Now, so order of growth and big O notation. I don't know if you already, if you still remember the discrete structure about big O notation, no? So, or you have already with your calculus, no? Algebra, no? Algebra, or either differential calculus or integral calculus, no? So, in estimating the running time of insert underscore sort or any other program, we don't know what the constant, say, or KR. We know that it is a constant of moderate size, but other than is not so important. So we have enough evidence from the asymptotic analysis to know that merge underscore sort, no, is faster than the quadratic insert underscore sort, even though the constant may differ somewhat. And this does not always hold, because the constant can sometimes make a difference, but in general, it is very good rule of thumb. No? So we may not even be able to measure the constancy directly. Let's say, for example, we may know that a given expression of the language, such as if, no, takes a constant number of machine instruction, but we may not know exactly how many. No? Moreover, the same sequence of instruction executed. Oh, wait. Okay, so we may proceed. No? So as I mentioned earlier, no, we may not even be able to measure the content of C directly. No? So a while ago, I will give you an example that we may know that a given expression of the language, such as if statement, takes a constant number of machine instructions, but we may not know exactly how many. Moreover, the same sequence of instruction executed on the Pentium 4 will take less time than a Pentium 2, although the difference will be roughly a constant factor. So these estimates are usually only accurate up to a constant factor anyway. For this reason, we usually ignore constant factor in comparing asymptotic running times. No? So an IT specialist have developed a convenient notation for hiding the constant factor. So let's say we write notation n or order n instead of Cn for some constant C. Thus, an algorithm is said to be O multiplied by n or linear time if there is a fixed constant C, such that for all sufficiently large n, the algorithm takes time at most Cn on inputs of size n. So an algorithm is said to be big O notation multiplied by n squared or quadratic time if there is a fixed constant C such that all sufficiently large n, the algorithm takes time at most Cn squared on input of size n, or big O notation multiplied by 1 means constant time. So a polynomial time means n raised to big notation O multiplied by 1, or n superscript of or raised to C for some constant C. Thus, any constant linear, quadratic, or cubic O, big O multiplied by n raised by 3 time algorithm is a polynomial time algorithm. So this is called big O notation. It concisely capture the important differences in the asymptotic growth rates of a function. So one important advantages of big O notation is that it makes algorithm much easier to analyze since we can conveniently ignore low order terms. No, let's say for example, an algorithm that runs in time 10n raised to 3 plus 24n raised to 2 plus 3n log n plus 144, this is still a cubic algorithm. Okay, so of course, since we are ignoring constant factors,
Hello, sir. Pa-mute po, sir. Salamat.
okay, so of course, since we are ignoring constant factors, okay, may two linear algorithms will be considered equally good by this measure. And there are even be some situation in which the constant is so huge in a linear algorithm that even an exponential algorithm with a small constant may be preferably in practice. And this is a valid criticism of asymptotic analysis and big O notation. However, as a rule of thumb, it has served as well. No, just be aware that it is only a rule of thumb. The asymptotically optimal algorithm is not necessarily the best one. And some common orders of growth seen open in complexity analysis. No, we have the constant, logarithmic. This will be the sequence. No, we have constant, logarithmic. When we say constant, big O notation multiplied by 1. When we say logarithmic, no, that is big notation O multiplied by log n. No, when we say linear, that is big notation O multiplied by n. Of course, we have also what we call n log n, quadratic, cubic, polynomial, and exponential. And of course, log means or log base 2 or the logarithm base 2, although the logarithmic base doesn't really matter since logarithms with different bases differ by a constant factor. We need to take note that all two big notation multiplied by n and O opening close parenthesis or multiplied by 2 raised to n are not the same. Okay? So we need to take note on that. I just want to play a video presentation wherein there is certain example, but I just want to start with the definitions of data structure and advantages, the data types, of course, the types of data structure up to the application of asymptotic analysis by solving problem 1 and 2.
In this presentation and in the subsequent presentations, I'm going to discuss about the basics of asymptotic analysis. And this is
Okay, so I'll just want to share a video presentation for you to understand more about the asymptotic algorithm. Okay, so this will be up to from the basic asymptotic analysis up to the sample solutions and computations and demonstration actually on how we'll be able to use asymptotic analysis.
just part one of that. So let's get started. I'm going to discuss the definition of data structure once again. A data structure is the organization of the data in a way so that it can be used efficiently. We want to use our data efficiently and we want to perform some operations on it. For this purpose, we are using the data structure which is efficient in terms of storing the data, and if we want to use our data, we would be able to use it efficiently. This is the definition I have taken from the previous lecture, right? Now this efficiently term is very important. In order to use data efficiently, we have to store it efficiently. There is no doubt about it. We have to store our data efficiently if we really want to use our data efficiently. Now let's discuss the efficiency in more details. Efficiency of data structures is always measured in terms of time and space. Let me tell you, when efficiency comes, it is always measured in terms of time and space. So what is the picture of an ideal data structure? An ideal data structure could be the one that takes the least possible time for all its operations and consumes the least memory space. Both these things should be less. It should take the less amount of time for all its operations and it should consume the least memory space as well. Then I can say a data structure would be an ideal data structure. Isn't that so? Now, our focus will be on finding the time complexity and not the space complexity, let me tell you. We are not interested in finding the space, that how much space a data structure will consume. We are right now interested in finding the time complexity for easing our task. Okay? So by finding the time complexity, we would be able to guess which data structure would be the best. Okay? Now, there is one question. On what basis we could compare the time complexity of the data structures? This is a very important question, let me tell you. We are going to compare the data structures, right? Now, how we can compare the time complexity of the data structures? On what basis we will compare it? We will compare the data structures on the basis of operations performed on them. Now, let me give you an example and the whole concept will be clear to you. Let's take an example of an array, okay? Let's say we have these many elements in our array. Right now, the size is not defined, but just think of this, that this array.
Okay, this will be an example of an array data sets, no, wherein we have 1, 2, 3, 4, 5, 6, 7, 8 datas, no? But we have an imaginary zero here, no? Based on the given array, value. Okay, and that is what we call null value with an array elements. Okay.
Is capable of storing 100 elements, and right now we have 8 elements in this array. Let's say our target is to add data at the beginning of the list. This operation we want to perform on this array. Array is a data structure. We want to perform this operation, that is adding data at the beginning of the list. And I want to know that how much time it will take. Let's study this properly. Let's say we want to add this particular element at the beginning of the list. Now, obviously this element is trying to reach this particular place slowly. There is already an element at the beginning of the list. Isn't that so? There must be an empty slot available in the array. As I have already told you, my array is capable of storing 100 elements. So obviously there is an empty slot over here. Now what we will do is, we will shift all the elements towards right. These elements we will shift towards right so that there should be an empty slot over here. Then we can easily add our element at the beginning of the list. Oh my god, there's so much hard work, right? If we want to add an element at the beginning of the list, and that too an array, it would be a very difficult task. We have to shift our elements towards right and then we can add our element. Let's take another type of a data structure, that is linked list. Linked list is nothing but sequence of nodes connected with each other. Here we have this node which contains some data and it also contains the address of the next node. Okay. Now the difference is that an array is stored in a contiguous fashion. That is, obviously if the address of this particular element is 1000, then the address of the next element will be 1004 if I'm assuming that size of integer is 4 bytes, right? But here it is not important. It might be possible that the address of the one node is 1000 and the address of the next node is 2000. It could be any address. It just stores the address of the next particular node so that it can be linked to the next node. So this is what a linked list is all about. And obviously there is a head pointer which is pointing to the first element of the list so that we can reach the first element and then after that we can reach the other elements as well. This is what a linked list is. Okay. Now let's say we want to add this particular data in the beginning of the list. Now how do we do that? We definitely have to store the address of this particular node over here, right? So let's replace this by 1000. Now by adding this address, it will point to this particular location. Now this node is linked to this node. After that, we just change the head pointer and it will now point to this particular location. With this idea, we would be able to add our element at the beginning of the list. Previously, the head pointer was pointing to this particular node. Now it is pointing to this node. This is the new node which has been added at the beginning of the list. Isn't that so? Is this operation tedious? No, not at all. This data structure is much efficient in adding data at the beginning of the list in comparison to the array. Isn't that so? So what is the conclusion? Inserting an element at the beginning of the list is faster in the linked list arrays. If you want to add data at the beginning of the list, then it is much faster in the case of linked list than arrays. In this way, we can compare data structures, and this will ultimately give the idea to select the best possible data structure for a particular operation, right? Obviously, in this way, we would be able to compare data structures, and then we can select the best possible data structure for a particular operation. Here, we are performing an operation that is adding the data at the beginning of the list. It is clear that linked list is performing better than array, right? So definitely we will choose linked list. So this way we can compare the data structures, and this will ultimately give the best possible data structure for a particular operation. That is why we are studying time complexity. Because with time complexity, we would be able to know that which operation on which data structure will take less time. In the subsequent lectures, we will learn more about the time complexity, how to find the time complexity, how to be able to compare the data structures. Obviously, the previous example was a very simple example. Sometimes it is difficult to understand which particular data structure is better than the other data structure. That is why studying time complexity is very important. This will help us in determining which data structure is better for a particular operation. Okay friends, this is it for now. In this presentation and in the subsequent, let's discuss part 2 of basics of asymptotic analysis. What we have learned so far. We have discussed what is efficiency in terms of data structures. Apart from this, on what basis we could compare the time complexity of the data structures. We have learned that on the basis of operations performed on data structures, we could be able to compare the time complexity of the data structures. But the question is, how to find the time complexity or running time of an operation performed on data structures? We know that on the basis of operations, we would be able to compare two data structures by comparing their time complexities. But how do we able to find the time complexity or running time of an operation performed on data structures? This is the question. Let's tackle this question by using some methods. And here is method number 1. Examine the exact running time. Now how to do that? Pick up some machine and turn the timer on. Run the operation for different inputs on the data structures. You want to compare one by one and see how much time a particular operation will take on these data structures. Obviously, the requirement is that you need a machine and you need a timer maybe. You just turn the timer on, and what you will do is you will run the particular operation for different inputs on one data structure, then in the other data structure, and so on in the same machine for the comparison purpose, of course. And then you can easily compare them because you have the time in your hand. You are basically running the timer. By running the timer, you would be able to compare their actual times. Isn't that so? So obviously you need to run the operation for different inputs on the data structures in the same machine, and you just have to turn on the timer for the purpose of knowing how much time a particular data structure is taking, right? In this way, you would be able to compare data structures, and obviously the one who takes less time is the best performer. For better analysis, you can compare the data structures on different machines too. But you know that there are some problems with this approach. It might be possible that for some input size, the first data structure gives the best performance, and for the other input size, the second gives the best performance. There's no way to know that basically. If you are calculating the exact running time, it might be possible that for some input size, your first data structure is actually giving the best performance and the other data structure is giving the best performance on the other input size. And obviously, it might also be possible that in some machine, for some input size of data structure, it is performing well, while in the other machine, the second data structure is performing well with a different size. Maybe it is possible that in some machine, your first data structure is giving the best performance, while in the other machine, the other data structure is giving the best performance. Exact running time calculation is not at all practical. Let me tell you, it is not at all practical. Okay. So examining the exact running time is not the best solution to calculate the time complexity. That's what I want to tell you right now, because calculating the exact running time is not at all practical. So what is the best solution to this problem? We'll see in the next lecture. Let's consider part 3 of basics of asymptotic analysis. From the last lecture, we have learned that examining the exact running time is not the best solution to calculate the time complexity. That's what we have learned from the last lecture, right? It is not a best practice to know the exact running time of an algorithm. So what is the best solution to this problem? There are certain points we need to note here. Measuring the actual running time is not at all practical. We have learned this already, that measuring the actual running time is not at all practical. The running time generally depends on the size of the input. I want you to note this point, that running time generally depends on the size of the input. Now why I'm saying this? Let's see this with the help of an example. Suppose we have an array which consists of 3 elements like this. Now what I want to do, I want to add one more element to the beginning of the list. Let's say this is the element I want to add at the beginning of the list. For this purpose, obviously, I must have an empty slot here and I need to make 3 shifts. Let us assume that if one shift takes 1 unit of time, then 3 shifts will take 3 units of time. Isn't that so? If one shift take 1 units of time, then 3 shifts will take 3 units of time. I need to shift each element towards right in order to make an empty slot here. Now you can understand that with the size equal to 3, the time will also be 3 units. After shifting, this will become empty and then I can add the element in the beginning of the list. There is no problem in adding this element, right? But what if we have 10,000 elements in an array? Isn't that going to be very tedious? Because shifting is costly, right? Adding the element to the beginning of the list is not costly. Shifting is costly. In that case, we have to make 10,000 shifts, which will take 10,000 units of time, because we have assumed that one shift will take 1 unit of time. We have to make 10,000 shifts. Therefore, it will take 10,000 units of time. So it is clear from this fact that running time generally depends on the size of the input. Here in this case, it depends on the size of the array. Size of the input or size of the array, one and the same thing. So if the size of the array is 3, it takes 3 units of time. If the size of the array is 10,000, it will take 10,000 units of time. The one thing we should note here is that it totally depends on the size of the input, that what is going to be the running time. Obviously, we are not considering the machine time, that how much time a particular operation will take in a particular machine. We are considering only the size of the input. So running time generally depends on the size of the input. This fact we should always remember. Therefore, if the size of the input is n, then fn is a function of n denotes the time complexity. So fn is nothing but a function which denotes the time complexity. It depends on input n. Okay? Or in other words, I can say fn represents the number of instructions executed for the input value n. Let's consider an example to understand this statement. Here in this example, I have a printf function within this loop which runs from 0 to n minus 1. Let's say this instruction will take 1 unit of time. This is my assumption. Let's say this particular instruction takes 1 unit of time. Then we are executing this instruction n number of times. So this is clear that fn will be equal to n. Because each instruction is taking 1 unit of time. And we are executing this instruction n number of times. Right? We are executing this instruction n number of times. That is why it depends on the size of the input n, and fn will be equal to n, because fn is keeping the count of the number of instructions executed for the input value n. This will give us the time complexity. But how to find fn? Finding fn in small programs is easy, but as programs become more complex, finding fn is not that easy. We can compare two data structures for a particular operation by comparing their fn values. We can compare their fn values and then we can compare two data structures. We are interested in growth rate of fn. This is very important. We are interested in growth rate of fn with respect to n. Because it might be possible that for smaller input size, one data structure may seem better than the other, but for larger input size, it may not. This is very important. We are interested in growth rate of fn. We have to try different values of n and then we have to find what is going to be the fn value. So for different values of n, we should calculate, not for just one value of n. Because it might be possible that one data structure may seem better for smaller input size than the other data structure. This concept is applicable in comparing the two algorithms as well. It's just like, we can compare two algorithms in the same way. We can compare two data structures in the same way. We are interested in growth rate of fn. Now, how to know the growth rate of fn? Let's consider one example. Let's say we have fn equal to 5n square plus 6n plus 12. This represents time or number of instructions executed. That depends on the input value n, of course. Let's say initially we take n equal to 1. Then percentage of running time due to 5n square will be 5 divided by 5 plus 6 plus 12. We just have to put 1 here. This becomes 5. This becomes 6. This is already 12. So 5 plus 6 plus 12. We will divide 5 by 5 plus 6 plus 12 and then we will multiply it by 100 in order to calculate the percentage. This will give us 21.74%. So we can clearly say that percentage of running time due to 5n square is 21.74%. 5n square is contributing this much amount of time. Obviously this we are calculating for n equal to 1. Let's see what is the percentage of running time due to 6n. It is 6 divided by 5 plus 6 plus 12 into 100, which is 26.09%. So 6n is contributing higher than 5n square, right? Now let's see what is the percentage of running time due to 12. It is 12 divided by 5 plus 6 plus 12 into 100, which is 52.17%. It seems like most of the time is consumed here. But wait, we have to see the growth rate. We cannot say right now that maximum amount of time is taken by this 12. Let's see for the other input values as well. Let's say n is equal to 10. In that case, 5n square is contributing 87.41% of the running time. You can clearly see the growth here from 21.74% to 87.41%, while 6n is decreasing. It decreases from 26.09% to 10.49%. And 12, which we thought of as taking most of the time, is now taking just 2.09%. Now let's take n value equal to 100. In that case, you can clearly see the growth. 5n square is contributing the maximum of the time. It is 98.79%, while this is just taking 1.19%, and 12 is just taking 0.02%. If you increase the n value further, you can clearly see 5n square is taking 99.88% of the time, while 6n is taking 0.12% of the time, and 12 is just taking 0.0002% of the time. These are almost negligible, right? Most of the time is consumed here, that is in 5n square. 99.88% of the time is consumed. So from this fact, it is clear that for larger values of n, the squared term consumes almost 99% of the time. This term is consuming the most of the time. Let's say you have taken the value of n equal to 1 and you simply say that 12 is taking the most of the time. But the reality is different. As you are increasing the value of n, you can clearly see which term is taking the most of the time. Now let's visualize the growth rate. Here you can clearly see that squared term is taking most of the time. The growth you can see clearly over here. While the growth of the constant term you can also see. Initially it is high, but later it declines faster. Similar for the linear term as well. You can clearly say that this squared term or quadratic term is taking the most of the time, right? So there is no harm if we can eliminate the rest of the terms as they are not contributing much to the time. We can eliminate these terms, 6n plus 12, we can eliminate them. There is no problem in eliminating them because we know that 5n square term is taking the most of the time. It is 99.88%. We are getting the approximate time complexity, isn't that so? And we are satisfied with this result because this approximate result is very near to the actual result. If we take fn is equal to 5n square, there is no harm. We know that it is taking 99.88% of the time, or it may take even more. We are getting the approximate time complexity and we are happy with it. There is no problem in eliminating the rest of the terms. This concept of calculating the approximate measure of time complexity is called asymptotic complexity. We are not calculating the exact running time here. We are eliminating the unnecessary terms. We are only concentrating on the term which takes most of the time. Okay? So this approximate measure of time complexity is called asymptotic complexity. And this is what we are interested in. We are not interested in calculating the exact running time. We are not interested in which machine we are executing our algorithm. We are only interested in calculating the approximate measure of time complexity. And we are satisfied with this result. We already know this fact that time complexity depends on the size of the input. As you increase the size, you can see the time complexity changes. So it depends on the size of the input and we are happy with this result. Okay friends, this is it for now. Thank you for watching this presentation. In this presentation, we will try to understand what is big O notation and how it is helping us in finding the growth rate of the function. So let's get started. Big O notation is used to measure the performance of any algorithm by providing the order of growth of the function. It gives us the order of growth of the function. That is what big O notation is all about. This notation is helping us in providing the order of growth of the function, how a particular function grows.
So a while ago, I'll give you an example in discussion about big O notation. So this will be actually a discussion in an example wherein you could able to apply the big O notations in asymptotic analysis.
It gives the upper bound on a function by which we can make sure that the function will never grow faster than this upper bound. So it gives us the least upper bound on a function so that we can ensure that the function will never grow faster than this least upper bound. We want the approximate runtime of the operations performed on data structures. We are not interested in the exact running time. From the previous discussions, it is clear that we are not interested in exact running time. We are interested in approximate runtimes. Big O notation will help us achieving the same. It gives us the approximate runtime. Obviously, it gives us the order of growth of the function, the least upper bound on a function, so that we can ensure that the function will never grow faster than the upper bound specified. Let's see the formal definition. If fn and gn are the two functions, then fn is equals to big O of g of n. If there exist constants c and n naught such that fn is less than or equal to c dot gn for all n greater than or equal to n naught. It says that we have two functions fn and gn. We are basically comparing these two functions. We can say that fn is equals to big O of g of n if and only if there exist constants c and n naught. We must have these two constants such that fn will become less than or equal to c dot gn, okay, for all n greater than or equal to n naught. So these are the two constants c and n naught. C must be multiplied by gn so that fn will become less than or equal to c dot gn, and this must be satisfied for all n greater than or equal to n naught. These two constants we have to find out. This simply means that fn does not grow faster than gn. Fn equals to big O of gn simply says that fn does not grow faster than gn because we are providing the upper bound on f of n, right? So it will never grow faster than gn. That's what this concept says. So we are basically providing the growth rate of the function, which eventually gives the worst case time complexity. Isn't that so? Because this is the upper bound on this function, which simply says that this function will never grow faster than this. And it means that we are actually calculating the worst case time complexity, how worst a particular algorithm can perform. Now let's see one example. Let's say fn is equals to n and gn is equals to 2n. We need to compare these two functions, let's say. We need to find is fn is equals to big O of gn or not. For this purpose, according to the definition, we have to write something like this. Fn is less than or equal to c dot gn. We need to find some c value here. Let's first replace fn by n and gn by 2n. This gives n less than or equal to c dot 2n, right? We already know that n is less than 2n. If we take c equals to 1 and n not equal to 1, this will definitely satisfy. So after replacing c by 1, this becomes n less than or equal to 2n, which is true. We can take any n value starting from 1, it will always satisfy. If we take n value equal to 1, then 1 is definitely less than 2. So for n not equal to 1, this will satisfy. So we have some constant c and some constant n naught for which n is less than or equal to 2n. So fn is equals to big O of 2n. Or in other words, we can say that fn function will grow linearly. We can replace this gn by 2n easily. Also, we can eliminate this constant term in front of this n because it doesn't matter if we eliminate it. Fn will grow linearly. And that is what is written over here. Obviously, it will grow linearly, right? Now let's see another example. Here fn is equals to 4n plus 3 and gn is equals to n. We need to find is fn is equals to big O of gn. For this purpose, again, according to the formal definition, we have to put something like this, that is fn is less than or equal to c dot gn. We can clearly see that 4n plus 3 is not less than or equal to n, but we need to find are they asymptotically equal. Let's replace fn by 4n plus 3 and gn by n here. After this, we get 4n plus 3 less than or equal to c dot n. We need to find some constant value c such that 4n plus 3 will become less than or equal to n. Let's take c equals to 5. Obviously, we need to choose higher value, right? Here it is 4n. Let's take c value equals to 5 such that it becomes 5n. then the inequality will be 4n plus 3 less than or equal to 5n. Now we need to find the constant n naught such that this will satisfy for all n greater than or equal to n naught. This means we need to solve this inequality. Let's solve this. 3 will be less than or equal to 5n minus 4n. This gives n greater than or equal to 3. So this inequality satisfies for all n greater than or equal to 3. Therefore, we can say Fn is less than or equal to C dot Gn for all n greater than or equal to 3, where C is equal to 5. Here you're choosing the constant C as 5 and n naught is equals to 3. Here this is the n naught value. For all n greater than or equal to 3, this will satisfy, which eventually means Fn is equals to big O of n. We can replace this Gn by n. Then this Fn will be equal to big O of n, which means that the growth rate of this function is linear. It will not grow faster than n, which simply means that the growth rate of this function is linear. It is not the case that suddenly it will behave like a quadratic function. It always grows linearly. And we can clearly see from this function as well. This is 4n plus 3. These are constants, right? And this is the n term, which is playing the important role. Fn equals to big O of n simply means that in worst case, Fn can grow linearly. Now let's analyze the growth rate visually. For this purpose, I have created this table for different n values and how Fn and Gn are changing with different n values. Let's plot this on a graph and this is what we get. This blue line, which is the light blue line, represents the Gn and this dark blue line represents Fn. This is linear growth. So the idea of big O notation is to give the upper bound on a particular function and eventually it leads to the worst case time complexity. Actually, big O notation is giving us this ensurety that this function will not suddenly behave like a quadratic function or a cubic function or will not grow exponentially in future. It just grow in a linear fashion. So the worst case could be a linear growth, not greater than that. This is the meaning of big O notation and this is how we are using big O notation to find the time complexity or the worst case time complexity of any algorithm of our choice. Okay friends, this is it for now. Thank you for watching this presentation. This lecture is in the continuation of the previous lecture where we have discussed about the big O notation and we have seen some examples related to big O notation. Here also we will see some examples related to big O notation, but we will also summarize what we have learned so far in asymptotic analysis. So let's get started. We are always interested in finding the growth rate of the function, isn't that so? We will take one function under consideration and we used to compare it with the size of the input. So as size of the input grows, how our function grows, we need to know that. For this purpose, we plug in different values of n into the function. N is basically representing the size of the input. We basically plug in different values of n into the function and plot a graph to know the growth rate of the function. But why do we need to do this? Why we need to find the growth rate of the function? Why is it so important? Let's see this why it is so important. Let's say we are comparing two data structures for a particular operation, okay? It might be possible that for some set of inputs, first data structure may give the best results. It might be possible that for some set of inputs, first data structure may give the best results, while for some other set of inputs, second data structure may give the best results. This can be the possibility. We can't simply predict that after which value of n, we can be sure that the one data structure will perform better than the other data structure. If you can't simply understand what I'm saying, then please see this graph. Here you can see that for n less than or equal to 3, Gn is performing better than Fn. Isn't that so? Fn is actually growing faster than Gn. But for n greater than 3, Gn is growing faster than Fn. You can clearly see that n is equal to 3 is the point after which we can be sure that Gn is growing faster than Fn. Isn't that so? Or in other words, I can say that Fn is performing better than Gn. So the value of n is very important here in this case. After that, we can be sure that which function is performing better than the other function. This is the reason why we are plugging in different values of n and are interested in the growth rate of the functions, representing the time taken by the operations performed on data structures. Because we are talking about data structures here, so we are considering the function as the time taken by the operations performed on data structures. Okay? But isn't it a tedious task to plug in different values of n and find the growth rate of the functions for comparison purpose? Obviously, it is a tedious task. You need to plug in different values of n. You need to determine the growth rate of the function. It might be possible that for n equals to 10,000, you will get that point that after which you can be sure that which data structure is performing better. It is very tedious task. Now here comes the big O notation to rescue. Big O notation helps us in finding the growth rate of the function without plugging in different values of n. That is the beauty of big O notation. Here we need not to plug in different values of n into the function in order to determine the growth rate of the function. Big O notation is the tool to find the growth rate of the function without plugging in different values of the size of the input. And the best part is it gives the least upper bound on the function, which gives the surety that the function under consideration will never grow faster than this upper bound. So what it gives the least upper bound on the function. Let's say the function under consideration is f. The least upper bound is g. So with this upper bound, we will be sure that g is always greater than f. Or in other words, I can say that g grows faster than f. With this, we can be sure that the function under consideration will never grow faster than this upper bound because the upper bound always grows faster than the function under consideration. So we can think of that least upper bound as the worst case time complexity of the algorithm. So the time complexity which we are considering is f of the algorithm, but the least upper bound, which is represented by g, tells how worst an algorithm can perform. So basically this is the upper bound which tells how worst an algorithm can perform. Let's see one example here. Here we have fn is equals to 5n square plus 4 and gn is equals to n square. Okay, we need to determine is fn is equals to big O of gn. That means we need to determine is gn is the least upper bound on fn. For this purpose, obviously we need to compare fn and gn like this. Fn less than or equal to c dot gn. If you want to know is fn is equals to big O of gn, then according to the definition, we need to compare these two fn and gn by using this inequality. Now let's take c equals to 6 and let's plug in the values of fn and gn here. We will get 5n square plus 4 less than or equal to 6 into n square. We are taking c equals to 6. Obviously we need to determine this constant, right? So we have taken it 6 because this is 5n square. This is just n square. If you put one greater value here, it might be possible that gn becomes greater than fn. Right now gn is not greater than fn, right? After this, we need to determine the value of n. For this purpose, we'll solve this equation. N square become greater than or equal to 4. And then after that, n becomes greater than or equal to 2. So it is clear from this inequality that fn is less than or equal to c dot gn for all n greater than or equal to 2. Here n naught is equals to 2, where c is equals to 6 and n naught is equals to 2. Here you can see the n naught value is 2 and c, that is the constant, is 6. So with these constants, we will get that fn is less than or equal to c dot gn. Here gn is representing the least upper bound on fn. So what we can say about this function? Fn is equals to big O of n square, which means that our function grows quadratically. So we can say that the growth rate of this function is quadratic. So this gn is basically representing the upper bound on fn, that is the worst case time complexity. This function will never grow faster than quadratic. It is not the case that it suddenly grows like, a cubic function. In the worst case, this is the time complexity, that is quadratic growth. Okay. Big O notation is simplifying the task, isn't that so? It eliminates all the unnecessary terms from the function which are not contributing much in the overall running time. In the previous example, you can see that constant 4 is not contributing much to the time, it's just a constant. While that n square is contributing much of the time. That is why big O of n square we get. So it eliminates all the unnecessary terms from the function which are not contributing much in the overall running time. Now, let's consider some growth rate of the standard functions. Here you can see these are some standard functions and here are their growth rates. Here you can see the values of n, that is 1, 2, 4, 8, 16, 32. You can clearly see that log n base 2 has the least growth while 2 to the power n has exponential growth. You can clearly see over here the value is 4 to 9 into 10 to the power 7 for n equal to 32. Here it is just 5. So we can compare these functions obviously. Basically we use these standard functions for least upper bound on a particular function under consideration. So we usually put them in place of gn. We can use log n base 2, n log n base 2, n square, n cube, 2 to the power n. These are different functions available which are also known as standard functions. Now let's consider one programming example which helps us in understanding how big O notation works in reality. Here you can see this program is used to calculate the sum of first n natural numbers. Within this main function I have declared three variables I, sum and n. After that I have a scanf function which is used to ask input from the user, that is n. After that we have this for loop and we will run this for loop from 1 to n. That means total n times, right? Here within this for loop we can see that one statement is there, sum equals to sum plus I. After this for loop completes, sum contains the sum of first n natural numbers. Isn't that so? Then we will simply print that sum on the screen. You can clearly say that first term is executed just one time, scanf is executed one time, this statement execute n times because this statement is within this for loop. This for loop runs from 1 to n, which means that this statement is executed n times. This statement just takes one time, this statement is executed one time and this statement also executed one time. Let's add them all up. This gives us fn equals to n plus 4. Fn keeps the count of number of instructions, isn't that so? That's also we have learned about Fn. By keeping the count of instructions, we are calculating the run time. That's an approximation obviously. So Fn is equals to n plus 4. Now, we know that Fn is equals to n plus 4. Let's take Gn equals to n. We are interested in finding the growth rate of this function. That's why we have taken Gn equals to n, which I thought of that as the least upper bound on Fn. Is Fn is equals to big O of Gn? That's what we need to find. For this purpose, obviously, we need to compare Fn and Gn. Here n plus 4 must be less than or equal to c dot n. We need to determine the value of c. Let's take c equals to 2, obviously because this is n, let's take it one higher. This will be n plus 4 less than or equal to 2 into n. Let me tell you that c value could be anything. That depends on you. I usually take one value higher than the value specified over here. So that is why I have taken c equals to 2 in this case. I'll simply compare n plus 4 with 2n. After that, what we will get is n greater than or equal to 4. So we can say that Fn is less than or equal to c dot Gn for all n greater than or equal to n naught, where c is equals to 2 and n naught is equals to 4. Here you can see n naught is equals to 4, c equals to 2. For these two constants, Fn is less than or equal to c dot Gn. So we can clearly say that Fn is equals to big O of n. We can also clearly see here that the growth rate can be linear only because the highest term here you can see is n. After that we have a constant term. So Fn grows linearly. That is why Fn is equals to big O of n. This is the worst case time complexity of calculating the sum of n natural numbers. But can we improve our algorithm? Let's say the program which is taking linear time is written by your friend. You need to write a program which performs better than your friend's program. For this purpose, you have written something like this. Here also, instead of running the for loop, we can simply use this formula, right? N into n plus 1 divided by 2. This will calculate the sum of first n natural numbers. Isn't that so? With this simple idea, we are actually replacing the for loop. There is no involvement of loop in this code, which is actually responsible for giving the linear growth. Here, all these statements execute one time. So total Fn is equals to 4. It's a constant number. There is no n in this case. Now as we know Fn is equals to 4, let's take Gn equals to 1. I thought of that this must be a constant. Is Fn is equals to big O of Gn? Fn must be less than or equal to c dot Gn. For this purpose, we'll plug in the values of Fn and Gn. We got this 4 less than or equal to c dot 1. Let's take c equals to 5. This will be 4 less than or equal to 5. So Fn is less than or equal to c dot Gn for all n greater than or equal to n naught, where c is equal to 5 and n naught is equals to 1. Then definitely we can say that Fn is big O of 1. That's the constant growth. So Fn grows in a constant manner because this is just a constant number. 4 is just a constant. It doesn't depend on the n value. So our Fn doesn't depend on the size of the input. So it is clearly the fastest algorithm among all. The algorithm written by you for calculating the sum of first n natural numbers is the fastest among all. Your friend has written an algorithm which has a linear growth. You have written an algorithm which has constant growth. So your algorithm runs faster than his algorithm. In this way, big O notation is very useful in determining the growth rate of the function. Not only that, it gives the worst case time complexity of a particular algorithm. So this is the beauty of big O notation. With big O notation, we can easily identify which particular program is better than the other program. Here we are considering two different programs. One has a linear growth and the other one has a constant growth. You can clearly say that the program written by you is the best and the program which is written by your friend is not. Okay friends, this is it for now. Thank you for watching this presentation.
Okay, so as our video presentation na demonstrate, no, it is important to each and everyone to understand asymptotic analysis because this will be a mathematical method used to study the behavior of functions as the input grows to infinity. So it's particularly useful in IT for analyzing algorithms and the efficiency of programs. So as our videos, no, there are three main types of asymptotic analysis, no. We have the big O, big omega, and big theta. So big O notation or O notation is used to describe the upper bound of the growth rate of a function. In other words, it gives an idea of how fast a function grows or how much time an algorithm takes in the worst case scenario. A lot of example stated earlier, but if function or f sub multiplied by n is big O notation multiplied by g multiplied by n, it means that if multiplied by n grows no faster than g multiplied by n for sufficiently large values of n. On the other hand, big omega notation o yung papaganin yung symbol na parang headset, no, is used to describe the lower bound of the growth rate of a function. In other words, it gives an idea of how slow functions grow or how much time an algorithm takes in the best case scenario. Let's say, for example, no, if a function n is big omega notation multiplied by g multiplied by n, it means that f multiplied by n grows to no slower than g multiplied by n for sufficiently large values of n. And big theta notation, yun yung O na may das sa gitna, no, is used to describe the tight bound of the growth rate of functions. So in other words, it gives an idea of how fast a function grows or how much time an algorithm takes in both the best and worst case scenarios. Let's say, for example, if a functions or f multiplied by n is big theta notation multiplied by g multiplied by n, it means that f multiplied by n grows at the same rate as g multiplied by n for sufficiently large values of n. Again, asymptotic analysis is useful because it helps us compare the efficiency of different algorithms or programs. No, if we have two algorithms A and B, and we know that A is of course big O notation and raised to 2, no, or multiplied by 2 or raised to 2, and B is big O notation n multiplied by n, we can say that B is more than efficient than A for sufficiently large values of n. So I think that's it for asymptotic notations.